So first thing we talked about, okay, in the chemistry unit here was day 1 when we went over structure of the atom and atomic theory. Okay, so let's first talk structure of the atom, right? What do I need to know about the structure of the atom?
Just protons, electrons, and
Protons, electrons,
negatron.
and what?
Negatron.
Negative. Close, it starts with N. Okay, protons, neutrons, electrons. Okay,
Yeah.
yeah, that's all right. We all talk about it. How do I figure out how many protons there are? It's the atomic number, right? Okay, so atomic number. Okay, what about electrons? It's the same, yeah, because the atom has to be electrically neutral, okay? So same as protons. Okay, calculating number of neutrons, that's a little bit different. Never looks right that way because it's not spelled that way. Neutral. Never looks right either way I write it. Okay, how do I calculate that? Right, atomic mass minus atomic number. Why is knowing that important? What am I going to ask you to do? Okay. Not so much complete the chart, but I'm going to ask you to draw a picture of an atom. Okay? And in that picture, I need to see the right number of protons, the right number of neutrons, the right number of electrons, and I need to see them in their proper locations. Okay? All right, so let's say just as a practice here, I want you to draw me, using our correct model of the atom, an atom of carbon. Okay, so I want to see an atom of carbon drawn using our currently accepted model of the atom. Give me a minute to get ahead of me on that one. Okay, so just so you know, on an exam there are no marks for artistic impression or quality. Okay, just I don't understand that stuff. I have no artistic sensibilities. Okay, all I'm looking for here, guys, is I want to see how many protons. 6. All right. And how many neutrons? 6, because 12.01. Yeah, 12.01 minus the atomic number 6 gives me 6.01, which means there's 6 neutrons. Okay, and they're all in the nucleus together. All right, I would probably even put beside there. See, I spell it differently every time I write it. That way I'm right half the time. Okay, proton, and I'll make that electron. Okay, just, you know, so a person who's looking at my diagram knows what I mean. Okay, where are the electrons? In the cloud. And there's 6 of them. In the cloud. Okay, so now I've drawn the electron cloud model, so I get a mark for that. Okay, I've got 6 protons, 6 neutrons, 6 electrons, and they're all in the right place. 5 marks. Okay, easy 5 marks on a unit exam. Spoiler alert, you're definitely going to have to do that on a unit exam. Okay. All right. We also talked that same day about atomic theory. Okay. Now, atomic theory was devised by whom? John Dalton. Okay, John Dalton came up with it. Okay, and he said it has 4 points. Should you know the 4 points? Yes, you should. Okay, so the 4 points of the atomic theory. Okay, Cole's Notes version. Okay, all matter made of atoms. Okay, second point, atoms of the same element are identical. Okay? When compounds are formed, atoms combine in whole number ratios. Okay. Okay, and the fourth point talks about what happens in a chemical reaction. Atoms can be rearranged, joined, or separated, right? But they can't be turned into other atoms. They also can't be destroyed, that's true, okay? But they can't be turned into other atoms, okay? So, in a reaction. Okay, I probably wouldn't have that be a multiple, or sorry, I probably would have that be a multiple choice question, right? You would just have to recognize like which of the following is not part of Dalton's atomic theory or something along those lines, rather than have you waste time writing it all out in a written response type of problem. Okay. All right. So we talked about Dalton, we talked about de Broglie's cloud model when we drew the diagram. Who's the other really important person? Okay, why is Rutherford important?
Because he found that nucleus.
Right. Rutherford proved the existence of the nucleus with his gold foil experiment. Okay, that's the other important person you would need to know. Okay, after that stuff, okay, we talked about naming. Okay, first step, if I want to write the proper name of a compound, so let's say I have that compound there. If I'm going to write its name, the first thing I have to decide is what? If it's ionic or molecular. How do I decide that? Right, if it has a metal in it, basically it's ionic, okay? Because molecular compounds are made just of nonmetals. So this is ionic because calcium is a metal. How do I know it's a metal? It's on the left-hand side of the staircase on the periodic table. All right, so I've got calcium here with phosphorus. Okay, if I'm going to write out the name of an ionic compound, our rules are that I write the name of the metal exactly as it appears on the periodic table. And what do I do with the name of the nonmetal? Add "ide" or end it in "ide." So this would be phosphide. Okay, do I need anything else? I need to check and see that this doesn't need Roman numerals. Calcium only has a charge of +2, so it does not require Roman numerals. Okay. Does it need prefixes? No, because ionic compounds do not require those. Okay, let's try this one. N2Cl5, ionic or molecular? It's molecular, okay? Nitrogen and chlorine are both nonmetals, okay? The rules for writing the name for a molecular compound are write the first element as it appears on the periodic table, okay? Does it need a prefix? Which one? Okay, it needs to be dinitrogen because there are 2 of them. Okay, and what prefix needs to go on the chlorine? Penta. And And how do I end chlorine? Ide. Right. Okay. Anytime you have a compound that's binary, okay, that's basically two things, it's going to end in ide. Right? If you have an ionic compound like this one, will that end in ide? And it won't because
It's a polyatomic.
it's a polyatomic ion. Okay, it's not just two elements anymore, it's three elements because one of these is a polyatomic ion. So it's still an ionic compound. I still follow the same rules. K stands for potassium. Okay, and what's CO3? Carbonate. Right. Okay, how did I know that I had a polyatomic ion that I needed to look for it?
Because both of the letters were capitalized.
Okay, both of the letters were capitalized, indicating that I had how many elements? 2. Okay, and in the whole compound I had 3. Okay, as soon as I have 3 or more elements, okay, in an ionic compound, okay, I need to look for my polyatomic ion. It's possible in a molecular compound to have lots of different elements, okay? You could have, okay, that's got 3 different elements in it, okay? But it's a molecular compound. How do I know it's molecular? There's no metals. I mean, hydrogen can act as a metal, but only if it's written first, okay? So, and the reason I picked this one is because it looks like it could be a polyatomic ion because, what does it end in? OH. It's tricky, okay? This is not an ionic compound because this actually isn't an ion, okay? It's actually bonded in, okay, there's an oxygen group and it's a weird molecule, but this is alcohol. This is the stuff that's in all the hand sanitizer we've been using, okay? Ethanol. Okay. What if I had this compound? What would I call that? Okay, it's ionic, so what's Mg stand for? Magnesium. Nitrate, right, okay, as soon as I saw that this was an ionic compound that had more than 2 elements in it, I knew I needed to go to my table of polyatomic ions and look for one of them. Okay, so that's magnesium nitrate. Again, didn't need anything else, no prefixes or anything like that. Okay, what if I have this one? Okay, is that ionic? Yes, copper's a metal, okay? And there's more than 2 elements in this, so it also has a polyatomic ion. What else is it going to need? Nope, actually it won't need brackets, but it's going to need Roman numerals. Exactly, okay? It's going to need Roman numerals in the name, okay? So I'm going to go name the metal, copper, name the non-metal, in this case the polyatomic ion, sulfate, okay? And copper can be a 1+ or a 2+, so I've got to figure out which one it is. Everybody with me there? Okay. How many sulfates are there in here? 1. Okay, that's a mistake a lot of people make. They see the 4 and they go, there's 4 sulfates. No, sulfate is SO4. Okay, that's 1 sulfate. If there were brackets and another number, there would be more than 1 sulfate. Okay, every sulfate has a -2 charge. Okay, which means the charge on the copper it's with must be +2 because they're 1 to 1. So this would be copper Roman numeral 2 sulfate. Okay, we have to be careful about when we apply the rules. Okay, I saw kind of on people's quizzes, I'm seeing either an under application of the Roman numerals, meaning you're just forgetting to put them in, okay, or an over application of them. They're everywhere. Okay, I'm seeing them in the formulas. I'm seeing them in the names. I'm seeing that's not what they're for. Okay? They're only to be used if I have an ionic compound and the metal has more than one charge. That's the only time. Those two things have to be true for a Roman numeral to show up, and it only shows up in the name next to the name. Okay? All right. I think that covers all the possibilities that we have covered in terms of naming. Okay, so just remember those are our rules. Okay, maybe if that's still something you're struggling with, try some more of the practice ones from the workbook, because I had like 5 or 6 naming sheets that I gave you in the workbook, and the key is posted a couple of Fridays ago now. Okay, in the stream, so you can always go back and find the keys and see if you're doing it right. Okay. Make sure you're working on those and practicing those, because they're not only important for reactions, but they're crucial for the mole equation as well. All right, after naming, we talked about properties of compounds. Okay. What kind of things do you think I'm going to ask on the unit exam about properties of compounds? Emma? Oh, sorry, I thought Emma had her hand up. No? Okay. See, boy, you better not go to an auction. You're going to buy something expensive. Yeah, go ahead. You.
Okay. So like, what property best indicates it?
Yeah, I could definitely have a multiple choice question like that. What property is going to always tell you something is ionic or molecular? A, observable properties. B, conductivity. C, pH, whatever. Could be something like that. Or I could give you a situational question, okay, in a multiple choice item as well, okay, or in a written response item, and say, you have a compound with the following properties. What is it most likely to be? If it's a multiple choice question, okay, you have some options there. If it was a written response question, it'd be a little bit tougher. You'd have to justify everything then. Okay? So if it was a multiple choice question, it'd probably go something like this. You have an unknown material. It is a red crystalline solid that dissolves easily in water. The solution produced easily conducts electricity, and it has a pH of 5. Okay? Is it A, hydrogen chloride, B, water, C, cobalt 2 nitrate, or D, nickel 2 chloride? Okay, which one would it be?
C?
Yeah, it'd be cobalt. Okay, cobalt 2 nitrate, I think is it. Okay, yeah, okay, that would be the kind of thing that I might ask. It's exactly what you were asked to do in your lab. I'm not going to ask you to do anything different on a test than I've asked you to do during the course. Okay, so that would be the kind of thing I might ask. All right, so we definitely need to know our properties of compounds. Just go over that lesson, okay, and be able to kind of apply what you learned in there. Right, and I would pick one that would be fairly obvious. It wouldn't be like ammonium nitrate, where it was small spherical crystals and they dissolve and they conduct electricity. They're practically neutral. Like I wouldn't make it something obscure. All right, when we did properties of compounds, we also talked about lab design, okay? And that would be, the most important part of that would be identifying the variables from an experiment, so kind of like scientific method type of questions. So I could ask you something like, here's an experiment. The experimenter's studying the effect of this on this, and here's their experiment. What's the manipulated variable? Okay, so maybe it goes something like this. A security engineer is designing a new type of bulletproof glass to use in banks. Okay, in his tests, he's laminating plexiglass with different materials. Each piece of plexiglass will be laminated with a different covering. In his experiment, okay, a 9mm pistol will be fired from 5 meters away at all pieces of glass, including a control where there's no lamination, okay? And the temperature will be the same for all of the pieces of glass. The plexiglass will be the same for all of them other than the lamination, blah, blah, blah. What is the manipulated variable?
Lamination.
Yeah, the lamination, okay? He's putting on a different lamination. What's the responding variable?
glass breaks or not.
Yeah, exactly, or the depth the bullet penetrates to, or whatever. He's obviously measuring something about whether the glass becomes bulletproof or not. Okay, so that would be his responding variable. What are his controls?
The how far the 9 millimeters away from the glass and the laminated, not the plexiglass has to stay the same.
The plexiglass has to stay the same. That's a controlled variable. Okay, like at least before lamination, so all the pieces have the same base glass. Okay, what else? And sorry, you said distance the gun is fired from. Temperature has to be the same because plexiglass can become brittle at low temperatures, so they all have to be treated the same.
The type of like gun or bullets that I shoot.
Yeah, the type of gun that he's shooting. I mean, if he shoots a water pistol at one of them, right, a BB gun at another, and kind of howitzer, okay, from a tank at one, it's hardly a fair test. Okay, so that would be the kind of question I would ask. Here's an experiment. Can you identify what the variables are? Okay. All right, and then solubility. That's the last thing that we've gone over here. Okay. Sorry, and polar nature of water. We'll talk about that as well. Okay, so solubility. What am I going to be concerned with in terms of solubility?
It precipitates.
Okay, so yeah, precipitate are basically all the terminology. Okay, just like your quiz yesterday. Okay, a lot of stuff is terminology, and not necessarily because I'm going to ask direct questions like, what, a solid is produced in a reaction that's not soluble. It's A, B, C, or D. And I might ask that, but I might not. Okay, mostly because I'm going to use those terms in the test. If you don't know what a precipitate is, you can't answer a question that has that word in it. Okay, so you definitely need to know your terminology for that. Okay, what else might I ask you about solubility?
What compounds are more soluble?
Yeah, exactly. I might give you a chemical reaction, okay, like on the examples, we'll have already gone over reactions by then, and say which of the products, if any, are soluble, okay, and be like A, compound A, B, compound B, C, both, D, neither, okay, or something like that. Okay, you would have to determine using your solubility chart whether something is soluble or not. So quick review here. Okay, your solubility chart has 3 rows. Okay, the top row has the ions, the negatively charged ones, okay, essentially like the non-metals or the polyatomic ions, okay, that we're dealing with, okay, and then there's the soluble row and the not soluble row. Okay, so if I give you this compound here, let's say, think of one that's going to work here. That's an easy one. Okay, so I say, is this compound soluble or not? All right, so you're looking at your solubility chart. You find chlorine to be right here. Okay, then you go down to here, and this says most, and this says and a few other things. I don't remember what else is not soluble with off the top of my head. Okay, is that material soluble? Yes, it is. Okay, if I give you this, okay, you're going to go, all right, so here's OH, it's soluble with, well, actually, it might say this, group 1, and list a few other things. What does it mean by group 1? Everything in the first column. Remember, the numbers at the tops of the columns, okay, indicate the group numbers. All right, so that's group 1, so it's soluble with group 1, but magnesium is not in group 1. It would be listed down here. Okay, or it might say most down there. All right, is that stuff soluble or not? It's not. Okay, so you'd definitely be expected to do that on an exam as well. Okay. And then we talked about water as a polar molecule. Sorry, what number are we on? Track here. 7. Okay. This I almost always make a written response in because there's some explanation required. It's hard to test this with a multiple choice setting. I expect that you be able to tell me what it means to be a polar molecule. Okay, that's one of the first things I would expect. What does it mean if you're a polar molecule? Peter?
Because of like certain elements and like their electron gravity or whatever they call it.
Electronegativity? Yeah.
Like some the electrons stay to one side of the atom and then the other, so one side is positive, one side's
Yeah, exactly. Okay, if you wrote that down, that would be worth a mark for sure. Okay, I'm looking for something about electrons are not shared equally in a molecular compound, okay, or in a covalent bond or something like that. It's a polar covalent bond. The electrons are not shared equally. If you mentioned electronegativity, great, but I don't think I would be really stuck on whether you mentioned that or not, just as long as you understood, okay, that in a polar molecule, okay, electrons are not shared equally, okay, and the second part that's important, okay, is that means, okay, 3 dots is shorthand for therefore, okay, so therefore, okay, one side of the molecule is positive and the other is negative. Okay, so that would be, this is what it means to be a polar molecule. Electrons aren't shared equally. As a result, one side of the molecule is positive, one side of the molecule is negative. Okay. Next thing we need to know, if one side is positive and one side is negative, what are some things that might happen?
Repulsion at the point of freezing for water.
Okay, for water, yes. Okay, so repulsion at the point of freezing is why water expands when it freezes. It's not true for all polar molecules, but water does do that. Okay, what does it mean for what two polar molecules can do to each other? What can they form? Okay, adhesion is one of the examples of this type of bonding. Hydrogen bonding, okay? So hydrogen bonding can occur. Now, hydrogen bonding is weak, okay? We have to remember that. It's not a strong bond. It breaks easily, but it also reforms easily, okay? Hydrogen bonding can occur, okay? And that means cohesion, okay, which is hydrogen bonding between like or dislike. Cohesive means to be, yeah, the same, like together, right? Yeah. So hydrogen bonding between like molecules, usually water. Okay, and the other one is adhesion. Hydrogen bonding between different molecules. Okay. 5-mark question. Okay, those are the points I would expect you to understand and be able to talk about if I'm asking you about what it means to be a polar molecule.
So, due to the fact that some molecules have a positive and negative side, do metals that act as magnets, are they polar as well?
No. No. If you have a chunk of iron, just one of its physical properties is that it's magnetic. Not all metals are. I can't, for example, I can't use a magnet to attach something to the side of my truck because I have an all aluminum truck. Okay, there's all these things, all these cool things that you can use on other types of trucks. It's just a magnet sticks to the side. I can't use that. Put it on, it just falls. Okay, magnets don't attach to it. So not all metals do that. And if it was about the charge, aluminum should be better at it because aluminum is always a 3+. Okay, but it's not. Okay, another thing to do kind of with solubility, but it's more of a practical application type of thing. I almost always ask, and I kind of call it the wheat from the chaff kind of a question. I want to separate who really knows their stuff from who kind of knows it. Okay, so I usually ask questions like practical application. So let's say you have a water sample, and you need to be able to drink it, but it contains a heavy metal. It contains lead. But I need to be able to drink that water. I can't drink it if it's got lead in it. Okay? How can I get the lead out? Okay, I could evaporate the water. Let's imagine that now I'm talking about the entire water supply of Calgary. It's all got lead in it. Because you're right. If I evaporated it, the lead would be left behind. That would be a good way to separate it. But if I'm talking about billions of liters of water, I can't. That's not a practical way for me to do it. Okay. So what's another way? Think solubility.
Add a solvent.
Okay. Not so much a solvent, because this stuff's already dissolved. Right? So I already have water as the solvent, but you're on the right track. I do need to add something. What's something we typically add to water when we treat it?
Chlorine.
Chlorine. Okay? All drinking water is treated with chlorine. Okay? We don't physically filter water. Okay? We don't run the entire drinking supply of Okotoks through a giant filter. Okay? It's not practical to do that. But what we do is we add chlorine for two reasons. Chlorine will kill most microorganisms that could make us sick. So it's a good way to kill things that, fever and stuff like that are going to be in our water. Okay? But the other reason we do that is if you look at your solubility chart, okay, and look at where chlorine is, look at what it's not soluble with. It's not soluble with lead, mercury. Okay, what else is in there? I think like cobalt or chromium, no? Lead, mercury, silver, copper, titanium. Okay? You don't want to have lead or mercury in your water. Those are like the two worst metals to have dissolved in your water. Okay? Especially lead. Lead can cause all kinds of developmental problems within the brain for growing children. Okay? This was a huge problem back in like I want to say like between 1900 and about 1965. Okay? There was lead in basically all paints, all wall paints. Okay? That would have been used in people's houses during that time. Okay? And as the paint would get old, it would peel. And little kids would peel it off the wall and eat it. I don't know why, but kids eat crap, like they just do that. Okay? And they would get lead poisoning. Okay? Not enough to kill them outright, but it affected the development of their brains, and they ended up with learning disabilities as a result. Okay? So you have to be careful what kind of things are in materials that could be ingested or around people. And a way to get lead out of a drinking water supply would be to add something it's not soluble in. Because as soon as I put something that has chlorine in it in the water, it'll cause a chemical reaction with the lead. It'll form a compound, lead 2 chloride, which will do what? It'll precipitate. If it precipitates, it will settle. And the clean water above can be removed. Okay? All water treatment plants have essentially a big settling tank, okay, that it happens after chlorine has been added. And all the heavy metals precipitate out onto the bottom of the settling tank, and water is drawn off from the top. Okay? And now all the heavy metals have been removed, and most of the bacteria are dead too. Everybody kind of with me there? Okay, so that would be kind of an application of solubility type of problem that you might get on a unit exam. Okay, that should cover most of the topics that we have done, okay, especially the most important ones, for the first third of the unit. Okay, the second third of the unit is all about reactions. So next week, we're going to start with the 5 reaction types, the basic 5 reaction types. Okay, we'll learn how to write them. We'll learn how to balance chemical reactions. Okay, and by the end of, not next week, but the week after, we'll be predicting the products of a chemical reaction. So all I would give you were the reactants, that's the things you start with, and you'll be able to, don't pack up, still got lots of time. I might still have things for you to write down, okay? So by the end, you'd be predicting the products of the reaction, balancing it, okay, telling me what type it is, all of that kind of stuff. And then we'll spend, after that, about a week, maybe a little bit more, on the mole equation, okay, which is our last thing in the unit. You will need to have a calculator, a scientific calculator, by then. Okay, so let's say by the end of the first week of October, you need at the very least a scientific calculator. Okay, it doesn't need to be the big expensive graphing one. Okay, you can just go to Wally World or the dollar store and get a cheapo scientific calculator. Okay, because it needs to be able to do exponents, and a typical one can't do that. So make sure you've got that soon. Okay. Any questions from you guys on the stuff from the first third? Okay. Well, you got a few minutes left in class here. Let's make sure we get our desks wiped down, and you can talk to your classmates or group mates from the lab. Okay. Maybe get some more of the unknowns figured out or something like that. Okay, but you got a little bit of time, so let's make good use of it. Okay, if you weren't here for the lab, it'd be a really good idea to talk to people who were. Okay, and just double check some things. No, I have no brand preference whatsoever. Yeah.